Good evening everyone, I am Mr. Ish. Thank you for joining me for this video, Integral Procedures. We're looking at one integral here in terms of the form that it has, the integrand form, but we're looking at it through three different intervals, and all of that will come into play with regards to proper and two improper procedures. I want us to look at these three distinct procedures so we don't lose sight of the big picture over here. When we're looking here at this specific form right here before us, from 1 to e, knowing that our graph very well will look something like this. We have a 1, 0 intercept, and the function will look like this. From 1 all the way up to e, this can be very well a limit representation and the area that falls right over here. We know we have nothing here with regards to an asymptote, a discontinuity, and an infinite interval, so we're looking at a clean proper integral over here, and the area of this has to be determined. It's not hard. And in this video, we're not going to be using any shortcuts. We're not going to be using any quick routines. We'll just go directly without skipping steps. We'll use a polynomial substitution procedure. If u is equal to ln x, du is equal to 1 over x dx, and then dx is equal to x du. You know you have a polynomial substitution with a definite integral, so you have to develop new intervals. u1 and u2 will be established based on this. ln x, ln of 1 is a 0, u2 will be ln of a e, natural log of a e as you know is a 1. Everything here becomes, with regards to these set of substitutions, becomes from 0 to 1. You have this ln x which has been substituted for u, you have an x below it, and then you have a dux. See, dux, this cancels out. You end up seeing a 1, 0 u du, which integrates to a u square over 2. And you know that's just a simple polynomial with a 1, 0. There's no need for you to resubstitute back the natural log, because then you'll have to go back to your original intervals. Anyhow, you put the upper limit, the lower limit, the difference of the two, you'll get 1 square minus 0 square all over 2. You'll have a area over here coming out with regards to what you see here, the shaded region, to be 1 over 2. This is the result of your definite integral procedure, and this right here, entire integral here, was a very proper integral. Do not let any other confounding variable come into the play in your mind and start dominating you with regards to everything we've talked about. Improper integrals, don't start looking at this and thinking improper integrals just simply because you have a rational function and you can develop an asymptote. That asymptote certainly develops, but it is outside this interval which has been presented, and there's nothing here with regards to an infinity in terms of an interval limit. Everything here is a proper procedure, a proper integral. For the next round, look, we've changed everything here with regards to the intervals, but nothing else has changed here with regards to the integrand. If you were to graph this out, you know we're looking here again from a 1, 0 x intercept. You have a function which will come like this, and here's my intercept. We're going from 1 all the way up to infinity, and you know you're looking at all of this shaded region going all the way up to infinity. Very likely we'll see divergence here, but let's see how it really plays out. Because we have an infinity over here, we can employ a limit. Limit as t will approach infinity. We're really looking at 1 up to t ln x over x dx. But you know we have to integrate that, so we bring the polynomial substitution technique. If u is equal to a natural log x, then du is equal to dx over x, and dx is equal to x du, right? You take this on the other side. u1 has to be established, and u2, everything with regards to this right here. u1 is a natural log of 1, which is a 0. u2 is a natural log of infinity. Well, we can't really do much with that. How about we just write here natural log of t, because we can do 1 and t. Natural log of t will be the same as natural log of infinity, but we'll play with this right here for the time being. Our everything becomes here limit as t approaches infinity. We're now plugging in the values. We have a 0, we have a natural log t, we have a u over here for natural log x, we have a du x over x. Remember, this is x du. This right here cancels with that. We're looking here at limit as t approaches infinity. We have 0 natural log t integral of u du. You know this u du will become a u square over 2, and you know we can put now this natural log t upper limit and 0 the lower limit. We can do that. When we put natural log t, we're getting a natural log t, and then we're doing a square minus 0 square and over 2. Remember I said we won't skip any steps, hence I'm not skipping any steps. Natural log t square is no different than you coming back over here and doing a natural log infinity square over 2. 0 square is meaningless. You can just remove that. This right here gives you a value in terms of infinity. Whether it's positive or minus, it really has no bearing. It's generally going to be a positive over here, right here. But your answer over here for this entire integral is that it diverges. You cannot do a clean representation here for the area represented here by the curve because of divergence. This integral diverges, and you have a type 1 improper integral at play over here. Now for the last example in this video, remember we were looking at 3, we've done 2, this right here is my last. We have from 0 to e natural log x over x. Here you know clearly you have a vertical asymptote x equals 0, and you know if you were to graph this, now you have an infinite discontinuity at play. You know you have 1 comma 0 x-intercept, your function will come like this and go like this. Of course this is exaggerated, but it's coming here up to e. You're looking here from 0 up to e, and your area gonna be here above the curve, and here area below the curve up to e. We have a little bit of a duplication here going with the previous video, but remember I'm showing you a broad integral procedure experience over here. That's why I'm utilizing the function we've seen before, because this one right here makes for an excellent learning tool. We have a 0 to e, we have an infinite discontinuity involved. Our interval here is really represented as 0 going up to e, including e, but not including 0. We can establish a limit over here. Limit as t will approach the 0 from the right, because it's going to be one-sided or right-sided limit only. You're coming here from t and you're going up to e natural log x over x dx. We have to do the polynomial substitution technique to handle this, because I don't want to do any integration shortcuts. U is equal to ln x, du is equal to 1 over x dx. dx is equal to x du. Establish your new intervals u1 and u2. Everything here with regards to what you see here. u1 will be coming here with the t and this. It'll be natural log t. u2 will be e, but will be affected by this natural log e, which is a1. You can come over here and let's do a limit as t will approach 0 from the right. We're looking here at natural log t. My u1 and my u2 is 1. And we're going here with the substitutions coming into play. U du x over x. This will cancel out. These x's will cancel out. And let's come right over here. Limit as t approaches 0 from the right. We have natural log t, and then we have 1. We'll have a u du. This u du is very easy to integrate. You know you'll get a u square over 2. And now we can abandon this limit and just look at this from lower limit natural log t, upper limit 1. You'll do 1 and then natural log t and the difference of the two, which I will now complete right over here. 1 coming in is no different than a 1 square over 2. I'm separating everything here under their own denominators. Minus and natural log t coming here square over 2. Now natural log t is what needs to be evaluated. We're looking right over here at this. This right here, natural log t 0 is no different than you plugging back the 0 and you're saying natural log of 0. But you know natural log of 0 is really a negative infinity. As your natural log function approaches towards this vertical asymptote, it dips down here towards the direction of minus infinity. This right here is no different than you just putting in here a minus infinity and squared. Anyhow, this right here will corrupt the entire, this right here will corrupt your entire integral procedure, such that you will want to just say your integral diverges. You cannot come up with a good area over here because of divergence. The limit will not exist particularly for this part over here, and this one can be evaluated, but what's the point in evaluating 1 over 2 when all of this diverges your entire presentation? Your answer over here is diverges or divergence. This limit as t approaches 0 from the right, for the technical perspective, it will not exist. Truly it won't exist because you're approaching minus infinity. Answer here, diverges, is right. So this is a type 2 improper integral due to the presence of an infinite discontinuity. So we've presented you 3 simple procedures here. One was a proper, one was a type 1 improper, and the third one was a type 2 improper integral procedure. And with that, let's wrap this video, and I'll thank you for watching. Have a good day. Bye.